Continuing along. So we can apply the same concepts of equilibrium that we learned in chapter 14 to weak acids and bases. Okay, so we'll start to refer to that as weak acid equilibria or weak base equilibria. So let's first start describing the weak acid equilibria. So here is a generic way to look at this reaction. And you can see we start to do that quite a bit as we advance in chemistry, so we can think of things generally. So here we've got H, which is my proton, and A, that A stands for anion, right? All of our acids are made up of a proton, H plus, and an anion, A minus. So just like I showed you in that reaction before, the the acid is a proton donor. So it donates the proton to H2O to become H3O plus, and it leaves that anion behind. It leaves it right there for A minus. Okay. So I could also write this generically as HA, aqueous, is in equilibrium with H plus and A minus. Perfectly okay to write the reaction like that as well. So now here we have a new equilibrium constant, Ka, where now the A stands for acid. We also often will hear this known as the acid dissociation constant. But more often in this class, we'll just call it Ka. Okay, the acid equilibrium constant, acid dissociation constant, Ka, those are all synonymous. And so now notice here that we can make an equilibrium expression for this. And we don't include the liquid water in the equilibrium expression, right? Because we don't include pure liquids. So now if I wrote the reaction like this, so I'll write or, so I'll put an or up here, okay? Or I could say Ka simply is just H plus times A minus, all divided by HA. And we'll use this form much more in this class because it's implied that water is there, okay? So now let's think about these equilibrium concepts for weak acids. So in a strong acid, Ka is large. And so that often means like infinitely large. So strong acids basically don't have equilibrium constants because strong acids just react in the forward direction to completion. But for a weak acid, Ka is small. And by small, we mean less than 1. Okay? Ka is much, much less than 1 for a weak acid. So that means for a strong acid, the equilibrium position is far to the right. So that means it reacts to completion. But in a weak acid, the equilibrium position is far to the left. And I'm just going to back up here to this one slide. So that's what we see right here. Okay? With this strong acid, there's nothing on the left-hand side. So that means our position is on the right. That means after the reaction's done, all of the mass is on the right-hand side of the reaction. But now you notice for this weak acid, right after it's done its ionization, almost all of the mass of the reactant is on the left. So once again, that's what we mean with this equilibrium position being on the left or on the right. Okay. So now what that means is the H plus concentration is basically equal to the initial HA concentration. So once again, we see that here on this figure. Okay. So this would be my HA, right? And so you can see before it's 0.1 molar, but then after the H plus is also 0.1 molar. Okay. So that's what that means. However, over here in the weak acid, the H plus concentration is much, much less than the initial HA. So remember, that little circle there means initial. So I'll just put an I for initial. Okay. So, and once again, we can see that in this graph right here. So you can see the H plus concentration is much, much smaller than the initial HA concentration. And that's just another way of saying the equilibrium position is on the left. So now this part gets a little bit confusing. So what do we mean by that? So A minus is a much weaker base than H2O for a strong acid, but for a weak acid, A minus is a much stronger base than H2O. So I'm going to write this generic acid, weak acid equilibria equation again, okay? And we'll attempt to describe that. So for a weak acid, A minus is a much stronger base than H2O. And actually, I should just write the full plus H2O just so we can do this exactly as that column says, H3O plus A minus. And we remember with equilibrium, we've got a forward reaction and we've got a backwards reaction. Okay, so once again, we remember that a base is a proton acceptor. Okay, so I'll write weak acid here. And so that means because a base is a proton acceptor and an acid is a proton donor, right? We remember this H3O plus, this is acid, so it technically is a proton donor. This A minus then would be a proton acceptor. And look, so what that means now, I'm going to redraw my equilibrium arrow. So you can see really that means this reverse reaction is far more likely than the forward reaction. So we often see the way these arrows are indicated tells us which way this reaction wants to go. Okay, so now we also know that to go forward, this H gets pushed over to that H2O. And so you can see here, this is why for a weak acid, this A minus is a much stronger base than this H2O, because this A minus wants to grab the proton from H3O plus much more than H2O wants to grab a proton from H. So that's why the equilibrium position is on the left, and that's why we see the reverse reaction dominating in this weak acid equilibria. Okay? So now let's look at a few example weak acids, and here's an example problem for you to think about. And by the way, anytime I do one of these example problems, I would encourage you to pause the video and see if you can work that out for yourself. And then, resume watching the video and see if you got the right answer. Okay, so I know that these are a little small, but hopefully you can zoom in and see them. We've got acetic, formic, hydrofluoric, hypochlorous, and nitrous. These are all weak acids. Here you can see their reactions in water. You will also notice when these are written, the weak acid, we keep its formula together. So, right, you remember that in the net ionic equation of a weak acid, we keep the acid formula together on the reactant side. Okay, so looking at this table, which is the strongest acid and which is the weakest acid? So all of these are weak. So let's write that. All are weak acids. However, within the family of weak acids, we can have varying strengths, and that's given by the Ka value. So the biggest Ka is going to be the strongest. The smallest Ka is going to be the weakest, okay? So we can actually see here this hypochlorous, so we're going to rank these things in order of strength. So number 1 being the strongest, we've got 1, 2, 3, 4, 5, and 5 being the weakest. So you can see this hypochlorous, because it has the smallest Ka, we're going to rank that number 5, so it is the weakest of all of these. Okay, so then what about the strongest one? Well, the strongest one is going to have the largest Ka value. And so you can see I've got a bunch of choices that are 10 minus 4. 4 times 10 minus 4 for nitrous, 6.8 times 10 minus 4 for hydrofluoric, and 1.77 times 10 to the minus 4 for formic. So hydrofluoric, that is in the number 1 position because that 6.8 times 10 to the minus 4 is approaching 10 to the minus 3, right? Okay, so now we know that that one is the strongest. So the second strongest is going to be the nitrous at 4 times 10 minus 4. The third strongest is going to be the formic at 1.77 times 10 to the minus 4. The fourth strongest is going to be the acetic at 1.76 times 10 minus 5. And then the hypochlorous was the weakest at 2.9 times 10 to the minus 8. So once again, these are all weak acids, but we can rank the weak acids in their strength in terms of their Ka constant. The bigger the Ka constant, the more protons that acid is going to produce, right? The more it reacts to completion, even though it doesn't go to completion, it just goes more. And the smaller the Ka value, the least protons it will make in solution.